Hello all. So now we are going to start our second unit, right? So in the second unit we are going to study about the combinational logic circuits. So far we have discussed in our first unit the basics of our the basics about our digital principles and system, right? So how the functions are going to be represented and how the internal representations are done using the various binary codes, so BCD, XS3 code and 8421 codes, various binary representations we study, and how the from the zeros and ones how we can obtain the Boolean expression, and how the Boolean expression can be represented in simple sum of product terms and product of max term, sum terms and all, and how the given Boolean expressions can also be minimized. So because we have to, as it is we are going to implement a Boolean expression into our system, the system cost is high because we have to use large number of without simplification. If we construct, we are in need of large number of components, right? So if we are simplify, the number of components used for a particular system is also going to be reduced. So for that we are going for the minimization part, and for minimization we saw the two techniques, right? One is a Carnot K map and another one is a tabulation method, right? And we also studied about all those we have studied because the internal representation, the internal processing is going to be done like this. So for that efficiency we have to build a system. So for that we are going to study this, and how the internally process all the outputs are going to be, all the inputs are going to be processed. So addition, subtraction, multiplication, division and all, how it is going to be carried out in binary way. That all we are studied in our first unit, right? So now in the second unit we are going to be saw the digital logic circuits we are going to be studying, right? So that is going to be we will see in our second unit. So the second unit is consisting of, so in the second unit we are mainly concentrating on the combinational logic circuits, because the digital logic circuits, it is mainly classified into two classes. One is a combination circuit and another one is a sequential circuit. So in the second unit we are going to be concentrate on the combinational logic circuits. So we have to first we have to going to study about the design and analysis procedure of our combination circuits. Then we are going to study about the BCD adders, subtractors and all, and then carry look ahead adders, manual comparators, and code conversion systems like circuits such as decoders, encoders, multiplexers and multiplexers. Finally we are going to study about the hardware description language, HDL language, and how the combination circuits are simulated using that HDL language. Yes. So this is our logic introduction about our second unit. So the logic circuits of our digital systems are classified into two categories, as we said. It is a combinational circuits and another one is a sequential circuits. So the combination circuits are nothing but whose outputs at any time depends only on the inputs at the present time. Okay, so if we are given a particular input, it will based upon the particular given input, it will respond a particular output, not based upon any other thing, right? So it doesn't have any memory elements. There is no storage devices are available in our combinational logic circuits. So it is designed using our gates and ICs. So examples of combination circuits include adder, subtractor, so as we parity generator checker, multiplexer, demultiplexer, encoder and decoders are some of the examples of our combinational circuits. So combinational circuit, as we said, so we have to given an input from our external source. Based upon the input, it is going to produce our output. So if we are having n inputs, it will have to equivalently for n inputs, it will produce n various outputs, right? So for a particular input A, there is a equivalent output A dash is possible, right? So if we are having a n input variable, then we have the how many bits are possible? 2 power n n possible combinations of binary inputs are possible, right? And for those each possible input combination, there is one possible output combination is also possible, right? So for example, suppose consider I am going to use a 4-bit combination of a binary input, right? So for 4-bit input representation, how many different possible combinations are available? 2 power 4, 16 combinations are available. For each 16 representation, I am having a 16 individual unique output representation is also possible from these combinational logic circuits. Yes. So now we are going to study about first we are going to discuss about the analysis of a combination circuit, right? So first what we are going to do this in the analysis part is, right, we have to provide it with the circuit diagram of a combinational circuit. We have to first identify whether it is a combinational circuit or a sequential circuit, right? So how we have to find whether it is a given circuit is a combination circuit or a logical or a sequential circuit. So sequential circuit which will have a feedback path, whereas a combinational circuit doesn't have a feedback path. So the difference between combinational circuits and sequential circuit is that combinational circuit produce a current output only based upon the current input we are given, whereas a sequential input we produce the output based upon the current input and the previous output value. Depends upon both these values, it is going to be produce a new output, right? And also sequential circuits contain memory elements, right? So whereas combination circuit, it is not there. Okay, so with this difference we have to easily find out. So for feedbacking the output to the for giving the previous output to as a input to the next output, the sequential circuit having the feedback path, whereas in the combinational circuit we doesn't have any such feedback paths are available. Only we are going to given a unique inputs. For that unique inputs, it is going to be produce the unique outputs, right? So that is a combination circuit. So we have to first given with a diagram. From the diagram we can easily find out the analysis the combinational given diagram by using the Boolean function or by using the truth table or by using the computer simulation. So the analysis is nothing but, so we are given with a diagram and we are going to find out what operation it is going to be done by this particular circuit is going to be identified. So that is also identified through the Boolean expressions, right? So that is the matter. So first we have to find out the given circuit is whether a combinational or a logical one. So as we said, how we can identify that this is a combination logic circuits, we have to identify whether there is any feedback path or memory elements is present. If it is not present, then we have to decide the given one is a combinational circuit, right? So then we have to, for all the input variables and the intermediate outputs and the final outputs are labeled with the arbitrarily meaningful names, and for each intermediate variables and output variables we have to form a Boolean expression in terms of input variable and a mixed mode, right? Finally we have to write the mixed mode information into a pure input expression with the only input variables, right? So after that, getting the input variables, we have to find out we have to derive the Boolean expression and simplify it and have to obtain the truth table, right? So this is the process. So consider this example. So this is an example. We have to consider the input contains only 3 variables A, B and C. So here I am, for my convention, I am naming the intermediate labels as T1, T2 and T3. Okay, I am naming this input as T1 and this is T2 and this is T3, right? And the final output as F1 and F2. F1 and F2 two functions, we have final output functions. Two functions are available. So now we are going to design. What we are going to do is, first we have to, this is a given, we have 3 inputs A, B, C and 2 binary outputs. Final outputs are F1 and F2, and we have to also label the various gate outputs as intermediate symbols called T1, T2 and T3 for our convention. We are using that, right? And we have to first derive the directly derived outputs. So T1 is directly derived and T2 is also directly derived and F2 is also directly derived, right? So what is a T1's expression? T1 is nothing but A, B, C, because we are using the AND gate, right? So T1 is equal to A, B, C and T2 is equal to A plus B plus C. And what is F2? F2 is this one is AB and AC, and this one is BC, right? By all the three outputs are, we are going to be sum up using the OR gate. So AB plus AC plus BC is F2's expression. So the directly derived information from the direct inputs are going to be derived initially, and with this information we are going to derive our next part. So final output we have F1 we are having. For deriving F1 we have to know what is T3, right? What is T3? T3 is nothing but from F2 they are having one link and they are negotiating it, right? So that is F2 dash ANDing with T2. So that is T3 is equal to F2 dash T2, right? So that is T3. And what is F1? F1 we are getting by using T1 and T3 are going to OR with T1 and T3, and we have to get F3. So F1 is equal to T3 plus T1. So now obtain F1 as a function of A, B and C, we have to follow the following substitution. So what is the substitution? F1 is equal to T3 plus T1, right? So what is T3? T3 can be represented by using F2 dash into T2. So what is F2? F2 is nothing but, we already know, AB plus AC plus BC is F2, right? So this is F2. So the whole dash it will contain the whole dash. So what does this whole dash contains? So this whole dash is nothing but, so here we have, for simplifying this, we have to apply the De Morgan's law. So what is the De Morgan's law? So De Morgan's law states that so what is the De Morgan's law? So De Morgan's law is nothing but A plus B the whole dash is equal to, what is it? A dash into B dash, right? Similarly, A B the whole dash is equal to, what is it? A dash plus B dash. This is a De Morgan's law. We are going to apply both here. So first A dash AB plus AC plus BC the whole dash, right? So first we have to apply, it will be changed as AB the whole dash into AC the whole dash into BC the whole dash. Yes, it will be changed like this. Okay. So if we have to convert this, again we have to apply this if then we have to again simplify this, what it will do. So A dash plus B dash, right? So that it is going to be done. A dash plus B dash into A dash plus C dash plus A dash plus B dash plus C dash into the T2 term, that is A plus B plus C plus T1 term, what it is ABC, right? So now we have to consider this is A dash plus B dash into A dash plus B dash. This is associative law. So through associative law, if we replace it, it will be becomes A dash plus B dash C dash. It will be becomes like this, and into B dash plus C dash into A plus B plus C plus ABC. So if we are again multiplying this with this, so it will becomes A dash into B dash this term, and A dash into C dash this term, and B dash C dash into B dash, it will become B dash C dash, because B dash into B dash it will become B dash, right? Anything B into B, it is equal to B. Okay, so that is B dash C dash, and also B dash into C dash, which is again becomes B dash plus C dash. So B plus B is equal to B, so that is 2 times B dash plus B dash C dash plus B dash C dash becomes B dash, one time one will be cancelled. So if we are multiplying this with this, so A dash and A, it will be cancelled, and A dash B dash B, it will be again cancelled. So A dash B dash C, okay, the first term, and the second term A dash A cancelled, A dash c dash c can, it will become 0, and so a dash b c dash, and then b dash c dash with a only. So a dash b dash c plus a dash b c dash plus a b dash c dash plus a b c. So this is the final output we got for our f1 output, right? F1 function. So now we get the f1 and f2 function, the Boolean expressions for f1 and f2. Now we have to construct the truth table from the Boolean expression, right? So we have 3 input variables, right? We have to listed it. So we have 0 0. So as per the 3-bit binary number, we have 8 combinations are possible. We have to list all those 8 combinations, and then first we have to derive the direct variables. The direct variables are t1, t2 and f2, right? So t1 it is abc and abc, and t2 it is a plus b plus c, and f2 it is ab plus ac plus bc. So applying the Boolean expression, the values in the Boolean expression, we got the output for t1, t2 and f2 like this. And f2 dash, so we have to determine the value of t3, we need f2 dash, right? So for that, we have from f2 we have to obtain f2 dash by negotiating the f2's value, and we get the values like this. And what is about t3? T3 is nothing but f2 dash t2, right? f2 dash t2. So we have to that is we have to adding f2 dash and t2, and we get t3 output like this. And finally we obtain now the t3 value. So from t3 we have to obtain f1 value. F1 is nothing but t3 plus t1, right? So we have to sum up these two values and get the values of f1. So that's all about analysis of combinational logic circuit. Similarly, we can also construct the truth table directly from the given diagram also. So not to directly derive the truth table, and from the truth table you can also obtain the Boolean expression for the output functions also. For example, so the method is like that. So without deriving the Boolean function directly, we have to first construct the truth table from the given logical diagram. So we have to first analyze how many inputs. For n inputs, we have 2 per n combinations are possible, right? So we have to list all the binary combination from 0 to 2 per n minus 1 in a table. Then label all the intermediate outputs and with arbitrary symbol, gate output with arbitrary symbol. So obtain truth table for the directly derived input variables. Directly obtain those arbitrary values that can be output values that can be obtained directly from the input variables are derived first. After that, the final output are derived from the intermediate values, right? So for example, consider this gate. So consider this logic diagram. So this logic diagram consisting of 3 inputs again, A, B, C. So we have 8 combinations because 3 inputs. So 2 power 3, it is 8 combination. So 0 to 7 we have to represent here. Then we have the output of this is going to be F1, and the output of this is going to be labeled as F2, and the final output of this Boolean this logical diagram is labeled as a Q, right? So first, F1 and F2 are directly obtained in terms of input variables. So we have to obtain F1 and F2 first. So what is F1? It is a NAND gate, right? We have a negotiation symbol with the AND attached. So this is a NAND gate, and this is a NOR gate, right? So we have to apply a NAND and NOR operation for A and AB. Here it is NAND of A and B, and here it is NOR of A and B. So we have to apply, and we get the output for F1 and F2 like this. And for Q, what we have to do for Q? So Q we have to AND F1 value, F2 value, and C input, right? So if we AND all these, we get a output of Q like this. Now if we draw a Boolean, came up for this Q, we get the Boolean expression for this Q, and we are obtain the final Boolean expression, simplified Boolean expression for our output variable q. Okay, so this is another method which we can directly derive the truth table, and from the truth table we have to draw this game up, and we have to obtain the simplified output expression for our boolean final output variable q. Yes, so that's all about the analysis of the combinational circuits. We analysis is nothing but we have to given with a diagram. First we have to analyze whether the given diagram is a combinational one or a sequential one. If it is a combinational one, then we have to follow the steps procedures. So what is the step? We have to first label all the output gates that are directly obtained from the input, and that now final output with the intermediate output labels, and then we have to derive the boolean expression for the directly obtained variables, and then the final output can be obtained in terms of the intermediate one. Then the final output can be replaced with means of our input variables. For that we have to make a substitution, and then we have to simplify the expression, and we have to come up with the boolean expression in terms of input variables. So after getting it, we have to derive the truth table for our from the boolean expression that we have obtained. Yes, so that's all guys, analysis of the combination circuits. Thank you.